All right, so I want to, before we actually look at calculating amounts of power, I want to address the efficiency of our wind turbines. I mean, it should be similar to hydroelectric, right? It's the same thing as hydroelectric, we just don't need the penstock. And how efficient is hydroelectric? Like up to 90 for new plants. But as it turns out, we're not going to be as efficient when we're talking about wind power. We just can't. If we were 100% efficient, that would mean that we have wind, it spins the turbine, and we've extracted all of the kinetic energy out of the wind. So those air molecules are just going to sit there, right at the turbine. And that would be a problem. If they're just sitting there, then the new wind can't really occupy that space, right? So we need to extract, we need to leave enough kinetic energy in that air to at least get it the heck out of the way. So the maximum efficiency that we could possibly do would be 60%, right? Any more efficient than that, the turbine's like not going to spin. And in reality, right, we do lose, like we can't even get, we probably don't get that much of the kinetic energy out of the wind. We are going to have thermal energy with the turbine spinning with the generator. So we're probably closer to like 20 to 35% efficient. Patrick?
Wouldn't that be the same thing with like hydroelectric if they were 100%?
It would, but if you remember, and I don't think I can easily pull the schematic back up, I'm remembering that after the turbine, there was an additional drop,
Okay.
right?
Yeah.
So, I mean, even if we did take all the energy out, well then there's still gravitational effect, and we'll still get it out of the way.
Okay.
Right. You're taking out, yeah, true, but we did say our starting energy was potential, and I'm not sure what the hydroelectrical engineers are using to calculate the efficiency. I don't know. All right, so let's get into the quantifying how powerful this thing is. Now we did quantify, right, how powerful our hydroelectric plants were, but that equation you had to be able to come up with on your own. Right? These ones are in the data booklet, but we still kind of probably ought to be able to derive them. So yes, the first equation in your data booklet for topic 8 is for wind power, right? But I do want us to see where those terms come from at least. So here's our wind turbine, and then there's kind of this like column, this horizontal column of air that's incident on our turbine. So this is like a three-dimensional or a two-dimensional cylinder. But then we have that third dimension as we come towards the turbine, right? So all of this air in this sphere inside here, right, is going to interact with the turbine blade, and that's going to be our source of energy, all right? So we're definitely going to need to care about this cross-sectional area, right, of that sphere. That's going to be one of our really important things. Kinetic energy of the molecules is going to be one of our really important things also. So the equation that we see in our data booklet only has 3 terms in it. Right? We have A, which is that cross-sectional area. And what is the area of a circle? Pi r squared. Right? So that's just going to be pi r squared, where r is the radius of the circle, which is also the length of the turbine blade. What is that? We saw this one last time. What's that? It's the Greek letter rho. What's it stand for? Oh, come on, really? Density, right.
Yeah.
But not density of water, density of who? Density of the fluid, density of air, right? Density of the air. And which is more dense, water or air? Water's way more dense. It's actually like almost exactly 1,000 times more dense than the air. So water was 1 kilogram per liter. Air is going to be like 1 gram per liter, right? Way less density. And then who's the V? No, not volume.
Velocity.
Wind speed. All right, that's the wind speed. You need to go? Great. All right, enjoy your break. All right, and again, just to kind of look at this diagram before we go back into looking at those terms. We have the higher velocity air here, right? It spins the turbine. We can extract maybe 20, 30, 35% of that energy. And then we have slower air on the other side. Questions so far? Okay. So as we already said, this area term is representing the area swept out by the turbine blades, which is the same thing as the the cross-sectional area of this sphere of air that interacts with the turbine. Now, I did just say a moment ago that the density of air was about 1 gram per liter. That's the same thing as 1 kilogram per meter cubed. Right? You do not have to memorize the density of air. I don't think you have to memorize the density of water either, but we want to be comfortable working with either of those units for density. And as we just said a few minutes ago, right, the main thing that would control this density would be your altitude. Right? Higher up will have a smaller density. And we could do something like this barometer to get some sense of if we have a high density or low density. All right, let's keep going. I skipped something. So let's work with one example right now of attempting to utilize this equation. Nah, I'm not ready yet. I'm ignoring the velocity cubed. Right, we already saw. Well, I think we can appreciate why we're using the area of this circle. I think we can appreciate why we're using the density of the air, because that's part of how many molecules are going to be pushing on the turbine blades, but I don't think we appreciate why we have the airspeed cubed showing up there. So in your 3-sums and 2-sum, can you take just 20 seconds and see if anybody has an idea for why the airspeed is showing up at all, and then why we're actually raising it to the 3rd power? Right, go ahead.
The airspeed at least is such a and the faster it is, the more power you have in it. And then I guess because it's like covering a certain area.
Why is it I don't know. Or why is it
Well, I know. Speed letters for power. My guess is
I'll give you a hint. This is part of one of the reasons.
I don't know.
All right. Anybody have any revelations here? So remember what we're doing with this wind turbine. We are converting kinetic energy from the air molecules into kinetic energy in the rotating turbine blade, right? And then spinning our generator. So this whole thing is going to be quantifying the rate at which kinetic energy from the air is delivered to the turbine, right? So how do we find kinetic energy? 1/2 mv squared. Okay, well there's our half. There's 2 of our 3 V's, right? And then mass is related to density. We said last class that mass is density multiplied by volume, right? So here's our density. I have that right? Yeah, density is mass over volume.
Yeah.
So our density's there. The volume is actually showing up in our cross-sectional area, but then we're missing the term for like the length of air, right? Which was kind of the frequency at which air molecules will collide. That ends up being our other V, is accounting for that 3rd dimension, right? So that's not a perfect derivation. That wasn't very clean, but I hope it lets you appreciate why each of those 3 terms. All right, now let's jump into this. We really do want to finish up today. So we have a wind turbine, bigger blades than we thought Freehold Township would allow. Like 45 meters is like about 140 feet, so it's pretty long blades. Wind speed 6 meters per second, so that's about what we saw we had at 80 meters high in Freehold. And air density is actually going to be pretty high, right? 1.25, so that's like a very, very high pressure day. Calculate the electric power that we could make if our turbine is 35% efficient. All right, so this should be a pretty straightforward calculation. We have our power is 1/2 the cross-sectional area times the density times the speed cubed. The area is our pi r squared. The radius of that circle is the blade length, 45 meters. We do have to square that though. Kilograms per meter cubed is what we want to use if our radius is in meters and our velocity is in meters per second. We definitely want meters to be our, we want kilograms per meter cubed, not kilograms per liter. And then 6 cubed. Anybody get that already? Not yet? 3 times 10 to the 5th. So what's that? 300,000 watts. And so Andrew got 300,000 watts. Can somebody confirm that?
Yeah.
So that's, most of our plants were in megawatts. So this would be a 0.3 megawatt power generator.
That's
I got like half of that because I don't think you divided by 2.
Oh, we didn't do efficiency. We didn't do efficiency. Ah. So that's.
I got it.
No.
With
All
alright.
yeah.
Well, can you give it to me without?
860,000?
Alright, so 860,000 is the total power delivered to the turbine. And then, yeah, we do have to divide that by the fractional efficiency or the relative efficiency to get the electricity generation. And then that's our. What? Oh my gosh, yeah. Alright, my brain is on spring break already. 300,000 watts, or 0.3 megawatts. So that does not compare very favorably to really anything that we've looked at, but I mean we usually don't have a single turbine. Right? We have like wind farms and we have pretty high density turbines. So if we had 20 of these, then we're at 6 megawatts. I mean that's something. All right, thank you for the help with that. Follow-up questions about that first example. Great. And this is kind of ideal, like 6 meters per second, I mean at 45. Well, 45 meter blades were probably only about 60 meters tall. That's faster than we're going to have here. 1.25, that's higher than we're going to have here. And that's with a good efficiency, right? So that's kind of idealized. All right, advantages, disadvantages. We'll answer a few more questions and then we'll jump into wave power. So we said a lot of these when we started power generation. Renewable, right? The wind is replenished, as we use it. So renewables are a great advantage. No pollution at all, right? No chemistry, no particulates, no greenhouse gases, no water quality issues. I'm saying here ideal for remote locations. So Liam was kind of arguing the opposite thing earlier. But if you live in Wyoming and there's very few people around within 100 miles, nobody's going to come build a big coal plant there, right? So you might have to use smaller scale things. Hi, did you think it's... Oh, I had her last blocked. Yeah, I know, it's not. Alright, sorry. Bye. Yeah. Alright, what else? Oh, and the wind is free. Yeah, Liam.
How much does it cost to build like a coal plant?
To build what?
Like a coal plant?
Oh,
boy.
It's gotta be $1 billion, or at least close to that. It's gotta be. I still haven't grabbed the picture. I bet you that picture's sitting on my what do you call it? My phone. No, what's my thing called that automatically puts the pictures onto my
PhotoStream? PhotoStream?
No, I don't use that one.
Dropbox?
Dropbox. It's probably sitting right in my Dropbox. Alright, anyway, those are the advantages I came up with. Disadvantages, right? Even, average wind speed is 6 meters per second. We don't always have that. Right? It's average. Sometimes there might be practically no wind at all. So if it's not windy, we can't make the power, obviously. I'm saying low energy density, and I think that's accurate. But really, the reason that's a disadvantage is we are going to have a lot of turbines if we're going to make a dent in the energy that we're using. Eyesore, I think that's ridiculous. I think they're pretty, but we've already talked about that the main reason why we don't have these offshore of New Jersey is that people don't want to look at them. Noise, I have not ever heard one. I tried to go, when I was in Oak Ridge, I tried to go on like an optional field trip to go look at some, but the people driving us there like almost killed us and we didn't like actually make it there. But you guys have heard them?
Yeah.
I don't think they made that much sense.
I don't think they make that much noise either, but I have heard like secondhand that they are pretty noisy. So what does that mean? I mean, that means like, fine, maybe if I own a farm and I have some put up, I just might not want to put too close to my house. I don't know. Isaac?
For another disadvantage, wasn't there a problem with wind turbines knocking bats out of the sky and killing them?
Yeah, okay, so I think in the earlier days, we did build turbines that spun a lot faster than the ones that we build today. So we did have problems with actually chopping up birds and insects and stuff. We don't have that problem anymore, they actually don't spin very fast. But Isaac is right, there is a problem with bats. Now, did your textbook talk about this? Three of you. There's a problem with bats because we are having a substantial drop in air pressure between we have a drop in air pressure behind the turbine, right? So a bat flies like tangent to like the wind, and they go from like regular air pressure and then they get into the shadow of the wind turbine and low pressure. Bats don't handle changes in pressure very well, and yeah, they can die because of that pressure change. So fine, there's not chemical pollution, there's not air pollution, but there is pressure pollution. But other than bats, I'm not really familiar with any other harm to wildlife. Ethan.
Oh, I was just gonna say that they're like really noisy.
Okay.
Yeah, like
Where have you been?
I visited Denmark, and Denmark like loves wind power, and you can hear them from like 100, 200 feet away.
But you're not gonna like typically be 100 or 200 feet away.
There are so many of them that you are like 100, 200 feet in
Yeah.
Denmark at least.
So it's like an irritant if you
Yeah.
happen to be very
They're
close.
also like really, really hard to transport.
To transport the electricity?
No,
Or
to transport the
the actual,
parts.
yeah, that's true.
Like they
They're
get caught up.
huge. That is true. And you don't want to assemble like small parts. You want to bring it in pretty well assembled.
So many
I got
traffic
you.
jams.
That's true. Jacob and then Patrick, and then I definitely want to move on to. Well, I want to have you answer a few more questions, then we'll move on to Wade.
Like wind turbines are really loud, especially once you get really close to them.
Sure.
Like they're dangerously loud
Okay.
at about 5 meters away.
Okay.
But 5 meters away from a coal power
Yeah, that's
plant,
gonna be
it's
pretty
also
loud.
pretty dangerously loud.
Yeah, absolutely.
And dangerous to breathe.
But you know, but one of the benefits that I didn't include up here, and the advantages is, like you can you can have the turbines there and still do stuff. Like if you're a farmer, you can have crops, like other than where the actual column is, you can have crops right there. It doesn't really block the sun. So yeah, you're right, but then that does sort of take away one of the advantages of being able to like multitask that length. Patrick?
Well, I think I heard recently they had like problems with like endangered birds, not getting like chopped up by them, but like just flying into them.
You know what? Bird's gonna fly into it. Evolution's not gonna let it last. So.
Can't control it.
Alright, sorry Liam, I'm gonna ignore you. I do wanna move on. So I just have a couple of questions I'd like you to answer in your 3-sims, 2-sims about the wind turbine that we're gonna install here. Right? So what would happen, to be as specific as possible, what would happen to the power we're generating if we did each of these 4 things, like separately? Like first we do this, and then we undo it, and then go back and do this. So have as specific of an answer as you can for each of those 4 things, and then in 90 seconds we'll compare.